Welcome to this web lecture dealing with electromagnetic waves and antennas. It forms part of the master course Microwave Engineering. In this web lecture we will discuss the history of electromagnetic waves. We will do it at a rather high level because it's meant as giving background information for following the course. We will look at the situation before and after 1800. Obviously something important happened in 1800. We'll get to that. We will look at the experiments performed by Oersted and Faraday. Then we'll move to the well-known Maxwell equations. And from the Maxwell equations we get to electromagnetic radiation, which we will explain in a graphical way. Before 1800, there was no continuous electrical energy available in the form of batteries. Experiments were conducted with big capacitors, mostly in the form of Leyden jars. So the experiments were not very scientifically sound and they could not be conducted in a repeatable fashion. What happened is that the experiments relied on sparks of electricity. And something changed in 1800. Before 1800, Galvani started experimenting with dissecting frogs. And in one of his experiments, by chance, he put a metal in the spine of the frog and another metal on a muscle and observed the contraction of the muscle. And he thought this was due to what was called animal electricity. And all over Europe, experiments were conducting with this animal electricity, and larger animals were killed on a large scale because people wanted to have more electricity. Luckily, in 1800, Alessandro Volta understood that it was a chemical reaction, and he constructed the first battery, the so-called voltaic pile, which consisted of discs of zinc and copper separated by moist clothing, and that produced a constant voltage, and suddenly experiments could be conducted in a repeatable way. So, where are we in history? Here, 1800. He was using a voltaic pile, had a current going through a wire, and saw that a compass needle in the vicinity of this wire deflected. The description of this experiment traveled through Europe, came in France, and that same year, Ampere understood how this worked, that the electrical current was inducing a magnetic field, and this magnetic field was deflecting this compass needle. And he even came up with a theory to describe it. Then, in 1831, Michael Faraday observed the opposite. We had seen that electricity could create magnetism. Michael Faraday did see that with magnetism you could create electricity. Michael Faraday, this is the man. This is the experiment. By moving a magnet through an electric wire in a loop, he could generate electricity. If you look at the picture, what the man is holding is actually a long solenoid coil for his experiment, and not what I thought as a student, a big cigar. In history, we are now here, 1831. To get the real connection between electricity and magnetism, because these two were only two observations, was made about 40 years later by a man called James Clerk Maxwell. I put it in red because this is very important. Maxwell united electricity and magnetism. This is the man. This is his earlier work. He discovered that the rings of Saturn are made of particles, and he also produced the first ever color photograph, of which you see a reproduction here. But we know him best for the Maxwell equations. Let's go through the Maxwell equations. And we use the Maxwell equations with the so-called nabla operator. What we see here is the electric field E and the charge ρ, and the nabla is defined as shown here, and it means a change in position. This first Maxwell equation is also known as Gauss' law. It tells us that an electric charge ρ creates electric field lines around it. Similarly, we have the Gauss' law for magnetism, which simply states that there is no such thing as a magnetic monopole. Then we have Faraday's law of induction. B is the magnetic induction. It tells us what we have seen in the experiment, that a changing magnetic field or induction creates a changing electric field around this magnetic induction. And then we have Ampere's law, which states that an electric current creates a magnetic field around this current. So where's Maxwell? The contribution of Maxwell we can find in a slight alteration of Ampere's law with big consequences. This is the change. What Maxwell did see was that a magnetic field cannot only be generated by an electric current, but also by a changing electric field. And this is very important. With this addition to Ampere's equation, he was able to unify electricity and magnetism, and he could prove that light is an electromagnetic wave phenomenon. And he also predicted the existence of waves at a lower frequency, the radio waves. Okay, one more thing about the Maxwell equations. Maxwell wrote down his theory in 1873, and the theory is still available in print and even to today's standards remarkably well readable. If you go through his work, you won't find the 4 Maxwell equations as we now know them with using the nabla operator. You will find 20 equations. The nabla operator we have to thank Oliver Heaviside for. From the Maxwell equations we have to go to electromagnetic radiation. Starting theoretically, we can show from the Maxwell equations that the source of electromagnetic radiation is the acceleration or deceleration of charge. We're not going to do that here. We simply assume that it is like that. And then we will give a graphical representation of electromagnetic radiation. We assume that field lines are continuous, and we assume that nothing can move faster than the speed of light, which are reasonable assumptions. And we look at a charged particle. We have a charged particle, we accelerate it over a certain amount of time, and we will look at field lines. From the starting point of the acceleration, we will have an observer traveling with the field lines, which are shown here for the starting position, and after the acceleration, the observer needs to be somewhere on this circle. We will look at the field lines after the acceleration. For the observer on the circle looking outwards, he has to see these field lines, because field lines are trajectories of charged particles in the neighborhood of the charged particle that we started with, and nothing can move faster than the speed of light, so these are the field lines the observer has to see looking outwards. Looking inwards after the acceleration time, he sees these field lines. But both field lines, the inwards and the outwards, are not continuous, and they have to be continuous. To make them continuous, we have to draw these field line sections, the so-called kinks. That's why this is called the kink model. And this is what the electric field lines look like. If we look at the charged particle at different instances of time, we will see the following development of the electric field lines. So what we actually see is a disturbance in the electric field moving outwards. Connected to these electric field lines are magnetic field lines that are perpendicular to these lines. So what we see is an outward going electromagnetic wave propagation. The maximum we will find in directions perpendicular to the acceleration direction, and in the direction of the acceleration itself there will be no radiation at all. Okay, where do we find this radiation in a real-life system? Well, let's look at this most general real-life system. Sources for acceleration or deceleration of charge, and thus of electromagnetic wave radiation, can be found at a change in wire radius, a reflection at an impedance discontinuity. It can come from the source directly. We will find it at bands, curves, or a reflection from the open end of a wire. And this brings us to the summary. We have seen the early history of electromagnetic waves. We have seen the Maxwell equations, how from the Maxwell equations we get electromagnetic radiation, which has been presented in a graphical way. And we have seen potential sources of electromagnetic radiation. Knowing now these potential sources of electromagnetic radiation will help us in designing antennas. Looking at antennas is the subject of a next web lecture, which I hope you will follow also. Thank you very much for your attention.